We're going to be looking at quantitative chemistry for AQA GCSE Chemistry Paper 1. As we go through this content, keep an eye on your exam. If the content is coloured in green, this is content that you could be assessed on your exam. While if your exam it is greyed out, it will not be assessed. You'll notice on each of the slides that we look at, there'll be a key at the bottom. Find your exam, but if this is in green, it'll be content that could be on your exam, or if it's grey, it will not be included. We're going to first of all start to talk about the idea about conservation of mass. And it's really important within your chemistry that you're able to interpret chemical formulas and use these because it'll be critical for your calculations. So for example, this formula here, our K2O, means that we've got 2 potassium atoms combined to 1 oxygen atom. So these smaller subscript numbers are giving us the number of atoms within the molecule. Now, sometimes we can find molecules that have got much larger formulas and have started to use brackets. Now, with this one, we've still got 2 aluminium atoms, but we now have a sulfate ion, this SO4, in a bracket, and we're told there are 3 of them. What this 3 is doing is multiplying everything within the bracket. So what this means is that actually I've got 3 sulfur atoms and I've got 12 oxygen, because 3 times 4 will give me 12. So any numbers outside of the brackets mean we multiply the entirety of the contents of that bracket by that number. With this then, we have the idea that there is this idea of conservation of mass. And this is the concept that atoms cannot be created or destroyed in a chemical reaction. Whatever atoms are going into that reaction are also coming out, just in a different form. What this means is that your mass going in must equal your mass coming out. Now, it does mean because of this idea, if we can't create or destroy atoms, that equations do need to be balanced. We need to account for all the atoms going into that reaction and coming out of them. So in this case, we need 2 H2, so 4 hydrogen atoms, and 2 oxygen atoms, making H2O, but 2 lots of it. But notice we've still got 4 hydrogens coming out and 2 oxygens coming out. Now these large numbers in front are known as multipliers, and what they do is multiply everything by their value that follows it immediately. Now the smaller numbers are subscript. When we balance equations, we cannot change those because it would change the actual substance that we had in the reaction. When we balance equations, all we can do is add multiplier numbers in front of our molecules. The subscript have to remain as they are. So there's a few little tips I'd say for balancing equations. I'd always say take each one in turn. Now in this equation, I would worry about balancing my oxygen last. The reason for this is notice that on the right hand side of the equation is split between 2 molecules. So if you try to balance this straight off, it can sometimes get a little bit tricky, especially in larger equations. So always start with the molecules that you've basically got the same, or just you find that you've got only 1 molecule on each side of the equation. So I start with my carbons. I've got 1 carbon in this molecule on the left, 1 carbon in this molecule on the right. They're fine, they're balanced. But next, I've got 4 hydrogens here and only 2 here. So I'm going to have to multiply this to make it turn into 4. So what I'll do is add a multiplier of 2 in front of the water molecule and turn this into 2 H2O. I now have 4 hydrogen atoms. Now at this point we're on to our last atom of oxygen that is split across 2 molecules. But over here we've got 2 of them. While on the right hand side we've actually got 4, so 2 here and 2 here. So what we'll do is now add another multiplier of 2 in front of our oxygen to turn this into a 4 also. And at this point we've got a balanced chemical equation. So one common calculation that you can expect to find in any chemistry exam is to find your relative formula mass of compounds. It's really important that you can identify your number of atoms that you have present in there, but my advice here is to be really systematic around how you approach the question. So with this, first of all, identify the number of atoms in this compound. So we've got potassium times 2 and oxygen times by 1. Then identify your atomic mass of each of these compounds. So here you look for your mass number in the periodic table, and sometimes in the exam question they might just give you the masses anyway. But if they don't mention it, this is where you go and find and use your periodic table. So in this case, potassium is worth 39 and oxygen's worth 16. So I've got 39 times 2 and I've got 16 times 1. Now we'll now finish off our calculation and add those values together. And relative formula mass tends to be pretty well done across most exam papers. It's, however, the starting point for a lot of the equations or calculations that we'll do after this. So it is sometimes a really common starting point within your exam. So if we look at this one, so this is now getting more complicated. The method we're going to use is still exactly the same. So we're going to identify the number of atoms in that compound, and we'll then substitute in the atomic mass of each. We'll go through, complete the calculation, and we'll add those values together, giving me a total relative formula mass of 342. So if we have a look at these ones, here following the same method, we've got 1 carbon and 2 oxygen. We'll substitute in our values, and this will give us a relative formula mass of 44. Here I've got 2 hydrogens and 1 oxygen. We'll substitute in our values for each of those atoms, and we'll complete this too. And the final one here for magnesium. So we've got 1 magnesium, 2 oxygen, 2 hydrogen. We've substituted in the atomic masses, giving me a total relative formula mass of 58. Although we've got this idea that mass needs to be conserved, and the idea that whatever the mass going in equals the mass coming out, sometimes the mass can appear to change. Now this tends to happen if one of the reactants or products is a gas that's not been measured at that point. So for example, here we can see the mass is decreasing. It's because of the fact that in this case we've lost a gas that must have been a product, and the gas has mass. So as we've lost it, the mass has decreased. If we tend to see that masses have mysteriously increased, it's because a reactant would have been a gas from the air that wasn't originally measured at that point, but has become incorporated into the new compound that's been made. So here our gas is a product, and so we've appeared to have a decrease in mass. If a gas is a reactant, we can sometimes see that the mass has increased. One little phrase that might come up is this idea around uncertainty. Now, if you're ever asked to find uncertainty, it might be 1 or 2 marks. For this, find the range of your values. So if you looked at your repeats, ignoring your outliers, what is your range? And you then divide that range by 2. So when finding uncertainty in a set of results, find the range of the results you're using and divide by 2. And your uncertainty will be plus or minus whatever that value is that you've just found. Moving on to higher only content, we have this idea in chemistry about moles, the unit of which is MOL. Now, when we're looking at moles, if we are given 1 mole of a substance, 1 mole of a substance's mass is equal to the relative formula mass in grams. So if, for example, we know that carbon dioxide has got a relative formula mass of 44, 1 mole of carbon dioxide would weigh 44 grams. Also linked to the higher here, we have this Avogadro constant. And this is a rule that says that in a mole of a substance, there must be 6.02 times 10 to the power 23 molecules in that mole. So if, for example, you have 1 mole of carbon, it will weigh 44 grams, and there will be 6.02 times 10 to the power 23 molecules within that. And that might lead to some sneaky little 4-mark calculations. So, for example, if we want to find the number of molecules in a substance, we'll use our equation moles is equal to mass divided by RFM. Now, Be prepared to remember that equation within your exam. So I would, even when you first go in, if you know, I tend to forget it, it might be worth writing on your periodic table as like a mental note. But moles is equal to mass divided by RFM. So if we know our mass in grams and we found the relative formula mass, you can calculate the number of moles that you've got. So in this case, carbon dioxide relative formula mass is 44. Moles is equal to this divided by its RFM. So it'll be 0.24 divided by 44. So actually, if we were given 0.24 grams of carbon dioxide, this is how many moles we've got. If they haven't specified around it, you wouldn't need to. But for example, I would do that to 0.0055 and round it. Now, if you are asked how many molecules were in this, now I know my number of moles. I will times this value by the Avogadro constant, and that will give me my number of molecules. Watch out, especially for a grade 8 or 9, if they asked you how many atoms were in there, you'd have an extra step. So that's how many molecules, but a molecule of carbon dioxide contains 3 atoms. So if we wanted to know how many atoms were in it, you would then have to times this by 3. But that would be a really sneaky little grade 8-9 question that they might do. But start with, if we ever want to know the number of molecules, we find our number of moles using the equation mass divided by RFM, and we times that number of moles by our Avogadro constant. If we have a look at this equation, we've already looked at the idea that we need balanced equations. But if we rephrase this equation shows us that 1 mole of magnesium reacts with 2 moles of hydrochloric acid to make 1 mole of each of these. We've been given ratios. We know the proportion of magnesium that needs to react with hydrochloric acid. We know actually needs to be twice as much hydrochloric acid compared to magnesium. We can use this as the basis of finding the masses of substances in chemical reactions. So for example, if we had 1,000 grams of magnesium, we could figure out how much hydrochloric acid would be needed. The important thing here, so it'll be worth a good 4 marks, is remember to use your equation moles equals mass divided by RFM twice. So first of all, we're going to find our number of moles for the thing that we know the mass of. So we've got 1,000 grams of magnesium. We can figure out how many moles of it we've got. So we'll do 1,000 divided by its relative formula mass of just 24 here. I know that we've got 41.7 moles of magnesium. Because we've got a balanced chemical equation, this does mean that we can start to figure out how much hydrochloric acid we've got. Because actually we know it's a 1:2 ratio. So if I've got 41.7 moles of magnesium, there will need to be twice that of hydrochloric acid. So we'll double that number to give us 83.4 moles of hydrochloric acid would be needed. And then we then go back to using our equation moles equals mass divided by RFM. We know our moles, we can find our relative formula mass, and as a consequence, we will be able to find our mass. So here's our moles from earlier. This is the mass of hydrochloric acid, or the RFM, and we'll rearrange. So mass will be equal to those two numbers multiplied together, giving me a mass required of hydrochloric acid of just over 3,000 grams in this case, so 3,044.1 grams required. So if we have a look at this one, it would be very unlikely to have to find the masses of multiple things, but if we look at worst case scenario, if we have 1,000 grams of carbon, we could figure out how much silicon dioxide we would need, and if we had enough of this, how much silicon and carbon monoxide we would need. So here we've got our RFM, first of all, carbon is just 12, and we'll figure out how many moles we've got. So in this case, 83.3. Now what we know, if we look at this ratio, is we've got a 2:1 ratio. We've got double the amount of carbon. So to find our number of moles of silicon dioxide, we're going to halve this. We can find its RFM, and actually that means that we can find its mass. So we'll substitute it into our equation, moles equals mass divided by RFM. We will rearrange. and then we'll find our mass. Now here we now know also that 2 moles of this makes 1 mole of this, so I'm going to have 41.65 moles of silicon. It is an RFM of this, and again we substitute back into the equation with our values to find that actually we should make this much silicon. Now 2 moles of carbon make 2 moles of carbon monoxide, so here if it's 83.3 moles of carbon, we should make 83.3 moles of carbon monoxide. We find its RFM, and we go back to using our equation, moles equals mass divided by RFM. So in this case, I'm going to make this much carbon monoxide. We can use moles as well to balance equations. So you might sometimes be given maybe a missing formula and asked to find balancing numbers. So with this, first of all, what's really important is that we need to be able to convert the masses in grams to amount in moles. So back to using that equation, moles equals mass divided by RFM. And what we'll then do is convert that number of moles to a simple ratio. So if, for example, we're told that 88 grams of propane reacts with 320 grams of oxygen to make this much carbon dioxide and this much water, find the balancing numbers. So you might be asked to prove this mathematically. So first of all, find your RFM of everything. So we'll need each of these in turn. So we'll identify a number of atoms, substitute in their values or atomic masses, and find our final value. And we'll then determine the number of moles of each. So at this point, we're going to do mass divided by RFM. So we know that propane's got a mass of 88. We'll divide it by its RFM. We've got 2 moles of it. Oxygen, let's take its mass, divide by its RFM. We've got 10 moles. And we continue to do this. So mass divided by RFM for each. Now, we're going to find the simplest ratio because they all have a common denominator of 2. So actually, the simple ratio is we've got 1 mole of this to 5 moles of this to 3 of this and 4 of this. And those are our balancing numbers. We don't have to write a 1 in front of it here because we don't include 1s within our equations. Sometimes a 5 and 6 mark question on the high paper might be to prove mathematically the limiting reactant in a reaction. And here we use a really similar process as earlier. We need to find the number of moles that actually we've got for a substance that's provided, identify our reacting ratios, and from this identify which one will run out first. So for example, if I've got 1,000 grams of magnesium, if we do moles equals mass divided by RFM, so that's my mass, I've divided by its RFM, I've got 41.6 moles of magnesium. With my hydrochloric acid, here's my mass of 1,000 grams, I'll divide that by its RFM, I've got 27.4 moles of this. And it's now figuring out, do I have enough? Now in the equation, we know that 1 mole magnesium reacts with 2 moles of hydrochloric acid. So if in theory we have got 41.6 moles magnesium, you need double the acid. And we don't have that. So we don't have the amount of, or the number of moles of hydrochloric acid required. It will run out first. This is the limiting reactant. When we talk about limiting reactants, it's the idea that in a chemical equation, if we add 2 chemicals together, one is going to probably run out first unless you've added really exact values. So the one that's in excess would continue to be there. If there were something for it to react with, it would. The limiting reactant is the one that runs out first and causes the reaction to stop. And it's known as limiting reactant because it's basically preventing any more product being made. It's stopping that reaction going any further. Now back to content for all. We all need to be able to do calculations involving concentration. And it's down to the fact that there's going to be an opportunity here to talk about different chemicals and the concentrations that they've got. With this, the concentration is measured in mass per given volume, normally in decimeters cubed. Now this unit for our concentration, grams per dm cubed, actually gives us the equation for how to figure this out. Now, the second equation that you must know for your chemistry is concentration equals mass divided by volume. Now, this is shown in our units here. So mass, grams, divided by dm cubed of volume. One little thing to watch out for, and it is very, very common, is be prepared to be asked to convert from centimetres cubed into decimeters cubed. And for background here, there are 1,000 centimetres cubed in a decimeter cubed. So if you do need to do a conversion, you divide your centimetres cubed by 1,000. On to only separate science. One of the ideas within chemistry is that reactions are not always going to give you exactly the amount of product you expect, and it leads to this idea of yield. Now, yield is the amount of product that we obtain in a reaction. But the reality is it's very rare to get 100% yield, and you might be asked for a couple of marks why this happens. So it's the idea the reaction might not actually fully complete. It may even be a reversible reaction, so it starts to go the other way. There is also the idea that some of the product or may be lost, or actually we may have it separated from the reaction mixture and not be able to obtain it and get 100% of the product we made. Now, what we also can sometimes find is the reactants can tend to react in ways different to than what's been expected. There might be something else in the container vessel, for example, that is reacted with as well. So those tend to be the three main ideas. The idea the reaction's not fully completed, the idea that maybe we've lost some of the product when we've separated it from the reaction vessel, or the idea that the reactants most likely reacted in other ways to what would be expected. Now, to find percentage yield, this is the mass of what you actually made divided by your maximum theoretical mass. So how much, according to the number of moles you had, you should have made. And we then times this value by 1,000. So it's the little number, how much you made, divided by the number that will always be bigger, how much you should have made, times by 100. So you should be given, if they want you to calculate the percentage yield, that they'll have to tell you. But you could, using your equation of moles equals mass divided by RFM, you could in theory calculate the yield that you should have got. So that you may be asked to calculate yourself. We also have this idea about atom economy, and this is a measure of the starter materials that actually end up as the useful product. Because we're not always going to have a reaction that just makes the reactant or the product that we want. It might make other things as well. Now, in terms of sustainability, we want something that's got a really high atom economy, in that the atoms we've put in end up being used for what we want them to be used for. Now, with this, atom economy is equal to your RFM of your desired product. So you identify right in that equation, what did I actually want to make? But we then divide this by the RFMs of everything that went into that reaction, and we times this by 100. Now, for separate signs, higher only. Not only might you be asked to do concentration equations in grams per dm cubed, but also you might be asked to do this in moles per dm cubed also. But not a lot's changed here. So this now just tells us the amount of moles of a substance that's dissolved within a solute. As the final bit of quantitative chemistry, we also have the amounts and volumes of gases that again can tend to be an extra mark or two in a calculation. So what we know is that we've got the Avogadro constant, that idea that in 1 mole we have a set fixed number of molecules within that. But if we've got gases, and we've got moles of gases, what we know is that 1 mole of gas, provided they're the same temperature and pressure, will occupy the same volume. So if I gave you, for example, 1 mole of hydrogen and 1 mole of oxygen, they would take up the same space. 1 mole of a gas takes up 24 decimeters cubed of volume. Now that is assuming that we're room temperature and pressure that is 20 degrees C and 1 atmosphere. So you might be asked to do a calculation where you figure out the volume of gas produced. Find your number of moles. Use your equation moles equals mass divided by RFM. But once you know your number of moles, if it's a mole of a gas, all you need to do to find its volume is multiply the number of moles by 24, and that will give you your gas volume.